Hi everyone, and welcome to the talk. So we're going to talk about state of crypto in Node.js today. It's a very serious talk, so I can assure you there will be no jokes. Yeah. And so I'm Ujjwal. You can find me on Twitter or GitHub at risercookin, or you could drop me an email if you like, snail mail, at risercookin@pm.me. So, okay. Yeah, state of crypto. Starting off with the code, few false ideas have more firmly gripped the minds of so many intelligent men than the one that if they just tried, they could invent a cipher that no one could break. And that's David Kahn from the Codebreakers. And I think this is a really important quote because it encapsulates the entire idea of this talk really well. In modern security, most of the ciphers, most of the systems that we would use are not secure in the sense that they're not like perfectly secure. There's no sense of perfect security today. What you would do would have relative security. And therefore, it's really important for you as developers to follow closely the state of this space in order to stay on the safe side of things, to make sure you're not using slow, deprecated, or insecure, flat-out insecure code. A little bit about me. I am a Node.js core collaborator, so I'm on the team, also on the crypto team, so that's where I'm coming from. I help maintain Electron. I work on V8 and TC39, especially with the internationalization spec. And I've worked with a couple of projects that go hand in hand with Node, so that's libUE. And I've also been a Google Summer of Code student and a mentor last year. So, disclaimer, what does crypto mean here? It is really important to understand what I mean by crypto, because when I say, do you want crypto, you absolutely want cryptography. What we're talking about is the crypto module in Node itself, the core module. So when you require crypto, that's the module you get. There's also a TLS module, but it's built by the same team. It's working with the same internals, so you might confuse the two, but we're not going to talk about TLS today. We will also not talk about cryptocurrency. So crypto is not cryptocurrency. Please, no. So why do you need crypto? And I've met a lot of people, especially web developers, saying, oh, I'm already using TLS, I do not need crypto. And that's okay. If you're developing for the front end exclusively, you might think that SSL or TLS is all you need when it comes to crypto. But as you might see, there's a couple of things from cryptography that you may need in any application. For example, encryption is one of those. Then there's key exchange, so exchanging public keys. There's cryptographic hashing that's used quite a bit. There's data signing to sign and verify data. There's pseudo-random number generation. That's also done quite a bit in front-end JavaScript as well. And there's interoperation with different crypto systems. So we'll discuss all of these, don't worry. Let's start off with encryption. So I guess encryption is perhaps the most commonly known about, most commonly used of all of these. So what is encryption? Encryption is encoding data. It's the process of encoding data to prevent unauthorized access. It's important because it upholds confidentiality of data or privacy of data if you're a human being. It is done in Node.js by using the cipher and decipher classes. So we have these two classes. One is called cipher, one is called one is called decipher, and you do encryption and decryption using the two of these. Now that's all good, but how do you make a cipher and a decipher? You have factory functions for doing that. So there's a createCipher method that you do to initiate a cipher, and a createDecipher method for doing the same to a decipher. Now that's interesting because I just told you that's the way you do it, but you should not do this. You should not do this because these are old methods that were introduced back in the day, and they miss a very important piece in encryption, and that is an IV. That's an initialization vector. By the end of the presentation, you'll have a fairly good idea what's so wrong with not using an IV. But for now, just keep in mind that you should probably always use an initialization vector when you're doing crypto. So there's that. It's perfectly clear at this point, but still, going with an illustration, here's plain text. You put plain text as the input to the cipher, you give it a key, and it converts that to ciphertext, which is what you transfer over the internet. And once you put that as an input to the decipher and give the key, it converts back to plain text. So that's nifty. How would you do that in Node.js code, though? So you will call createCipher IV with the parameters to initialize the cipher. So the first string argument that you see, AES192, that's the identifier that identifies the cipher you want to use. So here we use AES, which is the advanced encryption standard, with a key size of 192 bits. That's 24 bytes. And you put in a key and an initialization vector alongside it. And then in order to encrypt your data, you'd call cipher.update. So you put in the plain text there, and the next two arguments they don't seem self-explanatory, so I'll explain them. The first argument is the input format. So the input format might be anything your input is encoded in. If you read it from a file, it's probably UTF-8. In Russia, you might use a different encoding to support the Cyrillic characters, maybe. And you'd use that if you're reading from the file or from a string, encoded in that format. And the output I chose as hex, so it will output the bytes as raw hexadecimal. And then there is cipher.final, which you also gave the output encoding to, but it's kind of weird what it does. It does a lot of things, and we'll discuss that too in coming slides. Decryption is kind of the same. Instead of the plain text, you give it ciphertext. And if you notice, the encodings are all reversed, because now the input's hexadecimal, and the output, you need to get it in UTF-8. At the same time, you're using the same cipher. So that's convenient. Then there's key exchange. So why even bother with key exchange? Like, why do we need to exchange keys? We need to exchange keys because we need key exchange methods, because it's required to securely exchange keys over a public channel. Otherwise, you need a private channel to do that. And it's kind of inconvenient to like set up a private channel every time you need to communicate with somebody. So in order to exchange keys publicly, you need key exchange. Why even bother with that? It's one of the ways to agree upon a key before a conversation, which is like one of the most important steps to continue with the conversation. And it's done in it comes in two types. It's done by two methods. One is the prime number based. So it uses large prime numbers in order to exchange keys, should I say. And then there's elliptic curve based. So it uses different math, but the end result is the same. Now, how would you do that in Node? You have the Diffie-Hellman class, which helps you do the prime number based thingy. And there's an ECDH class, which is the elliptic curve Diffie-Hellman class, for short. And it will help you do the elliptic curve, use the elliptic curve algorithms. This diagram illustration should explain how it works. So there's two parties involved. There's Alice and Bob. Alice computes her secret key in private, which is KA. Bob computes his secret key, KB, in private. and they don't share these with anyone. They have a publicly known variable which they operate over their personal keys, and then they send pKa and pKb to each other. Now this is special because the operation used, the prime number base or the elliptic curve, needs to not be reversible. So anybody who's who's eavesdropping on the conversation cannot determine Ka or Kb from these. So like, it's pretty useless for anybody eavesdropping on them. Then when Alice gets the result from Bob, she operates her key on it, Bob does the same, and they both get a common encryption key, and the eavesdropper got absolutely nothing of use, obviously. They still have pKa and pKb. Now, this looks a bit wordy, but this is how you do it in Node.js. You'd make a variable for Alice, which makes a Diffie-Hellman class instance, and you specify the max number of bits that you want to go with. So it's 2048. You just initialize that. Now you initialize Bob with the same prime and the same generator than what Alice used, and you generate Alice's key, step 1, Bob's key, also step 1. Then they compute their secrets. So they exchange their keys over the internet maybe, or some other medium, if you do that. And Alice computes her secret using Bob's key, and Bob computes his secret using Alice's key. And if you call assert.strict equal or something like that, they will be the exact same thing. So key exchange. Kind of absurd to do it in one script, I know. But ideally, you would have like 2 different computers, 2 isolated computers connected only over the internet doing that. It's just a proof of concept. And it's similar with ECDH. So you tell them which specification to use. So here we're using P256. Same with Bob. So you just initialize the 2 objects. You generate keys for Alice. You generate keys for Bob. Alice computes her secret using Bob's key. Bob computes his secret using Alice's key. And they're both the same. So that's how you do key exchange. Moving on to hashing. So just a quick question. How many of you have heard about hashing or done any hashing? That's almost all of you. That is because it's one of the most common things that you do in and out of cryptography. And hashes are like the most common primitive used of all the primitives we'll talk about in crypto. So hashing, if you didn't know what it is in the minority, is the use of hash functions basically. So what do hash functions do? They map arbitrarily sized data to fixed bit strings. So you take an input, which could be any sort of input, like it could be however big, and it just maps that to a fixed size string, which is the output hash. The deal is, it could be very unsafe still, even if it satisfies this property and is a valid hash function. That is why we cannot use just any hash function in cryptography, and we'd use something which we might call a cryptographically safe hash function, which has 2 extra properties. It must be super hard to invert it, so there's possibly no way to go back from the hash to the original value, and it should be collision resistant. So it should not have any known collisions. It should not have any 2 known inputs that are known to produce the same output. And that is one of the reasons why you should not use something like SHA-1, for example, because SHA-1 has a known collision. You're fine if you use SHA-2, though. So we'll come to that. And hashing it upholds 2 different principles of information security. It upholds authentication and integrity. And I think we've all dealt with the integrity part in the past. We've like downloaded files from the internet and computed its checksum just to verify if it's the same file. So that's that. Now hash functions are also, hashing is also much more common than all other things, because like they're not an entirely a different crypto system in themselves. They are more like cryptographic primitives that you'd use inside of some other bigger crypto system. So they're used for data signing quite extensively, and they're using for hash-based message authentication systems. So that's HMACs. They're used for a lot more things, though. You might have known a couple of them, but those are some of the most common cryptographic uses of hash functions. Now, in Node, you'd call the hash class to do any of the hashing. And there's an HMAC class, which is like a more specific version of the hash classes. Does the HMAC thing for you so that you don't, it's more convenient to use it. This is just like simple illustration, a hash function taking in a message and converting it to a hash value. It's fairly simple to use the hash. You might see the pattern here, create space, create, and then the file name, then the class name would create an instance of that class. So create hash will create a hash object. And you specify the hash function that you want to use. In this case, we use SHA-256, so that's SHA-2. And you should be fine using that. Then you call hash.update with some value. That is the data that you want to hash. And when you console.log that result, calling hash.digest, it would produce the result of hashing that value. You also need to pass in the output format. So we wanted a hash in hexadecimal. That's usually the kind of format that you want your hashes to be in, hexadecimal strings. HMACs work exactly the same. They just have one additional input, which is a secret that you might use to check, to verify the hash. So it not just verifies the input, but it verifies the combination of the input and the secret. So that helps with authentication. Now, moving forward to data signing. Data signing is a really important function of cryptography. And if you're disappointed that I'm not talking about cryptocurrencies, this is very prevalent for cryptocurrencies. It's really important that you sign your transactions. What is it, though? It entails presenting the authenticity of digital messages and documents using digital signatures, as you'll see. And it upholds three tenets of information security as well. We already talked about authentication and integrity. It also has the third thing, which is called non-repudiation. Now that means that once you sign something, you can't, how do I put it, take it back. You can't go back on it and like, yay, I did not sign this. And this is kind of what we use physical signatures for, right? You sign a document and it's like, yeah, I've put my signature on it. So that's what gives the digital signatures their nature of being a digital signature, I guess. And it's used, it's done using the sign and verify classes in Node. And here's a simple illustration explaining how internally you would hash something. It's just hash something and then you produce the signature from that. So you hash a file to get its hash, and then you encrypt it using the encryptor's private key to produce the signature. Appended with the file, that's called digitally signed data, and it's very convenient for the other party to just disassociate the two and do the exact same thing on your data just to ensure that it has the same valid signature. How would you do it, though? So, as common, you call the createSign method. All it needs to take from you is the name of the hashing algorithm that it needs to use internally. No other parts are like moving parts, but this you could specify. And you just then call sign.update, which updates the sign object with the data it needs to sign. And so you see get private key. Now that's not a valid JavaScript function. It's just, it just signifies that you'll have to do something in order to get the private key. Maybe you'd call it from a network. Usually what you would do would be to store it in a PEM file maybe, or a DER file. So those are the two ways we store digital signatures. And you would read that from the file system. So you'd read the file and get the private key. And then if you call the sign.sign method, that with the private key and the output encoding, it would produce the signature. So that's the signature variable. And once you have the signature, and you don't need the private key, you need a public key to verify stuff, because it would be bad if everybody knew your private key. But so you create a verify object with the same hashing algorithm. SHA-256 is a better bet. And you verify with the same data. You update verify instance with the same data, and you get the public key, and then you call the verify method on the object. And that would tell you if it's the signature is verified or not. Here it outputs true, so you know that it's verifying. Moving on to pseudo-random number generators. So most random numbers are like very common. We've all used and played with random numbers. They are they're important for the function, for the perfect functioning of a lot of crypto primitives as well. And which are these? So cryptographic applications require random numbers. You need random numbers to generate random keys and other moving parts of key generation. You need to generate initialization vectors. So if you had a doubt about how to get the IV in the first slide, that's how you get it. You make a random IV. IVs do not need to be secret. They just need to be random and unique. So a random number generator helps with that. You also have to generate salts sometimes. They are like actual physical salt. They're sprinkled on top of a hash function to make it more secure. And one-time paths. So if you've played with one-time paths in the past, Claude Shannon says apparently that in order to reach perfect secrecy, you need to use one-time paths with completely random keys. So you'd need random generators for that. Now math.random, I guess we've all used math.random sometime in the past. And just to point out that it's not a great idea to use math.random, especially for cryptographic applications, but sometimes for other reasons as well. That is because math.random does produce random numbers, but it has no security guarantees. It's completely reversible. People have had proof of concepts that could like completely break it and predict it. And honestly, you don't care about it too much on your Gallagher cron to see if like people could predict where the enemies would spawn. But if you're building something like a cryptographic application, you do not want people to intercept and guess what numbers are going to come up. You also do not want to use them in, for example, multiplayer games, because it would be unfair if somebody guessed the random numbers. So you need higher entropy as well. Math.random uses a very low entropy source. It uses the system date and whatnot. Please do not use math.random. How to actually make true random numbers? Using Node, you use the two functions, random bytes and random fill. So, and Robert Arcavu says, the generation of random numbers is too important to be left to chance. And he's right. So, how you do random numbers using random bytes is you could do it synchronously, just call the random bytes function. It's probably the simplest. You specify the number of bytes you want to produce, so it returns a buffer, which you could then print out and check. It also works asynchronously, so if you give a callback, it would pass the buffer to the callback instead. And you also get an error, which you could handle. I don't have enough space to do that. Random fill works similarly. It's quite the same thing. Just unlike random bytes, you don't have to give a number of bytes to produce. You just create your own buffer and pass the buffer, and it will like fill the entire buffer. So the way we've done these both, they're exactly the same. Now moving on to interoperability, and it's not the kind of thing that a lot of you might care about, but it's important to interoperate with different crypto systems and different services running maybe very different stacks. For example, in production, you might be doing something with Node in one service and Python in another service, and you want the two cryptographic primitives to actually go well with each other. So there's a great number of crypto libraries, and some of them are really good. You might want to use them. There's Bouncy Castle if you're into Java and C#. There's Salt for C. There's Lipsodium for C as well. And there's PyCryptodome for Python. And there's like a lot more, but it's like, I could go on. Node.js uses OpenSSL. It uses none of these. OpenSSL is also very good. We'll discuss about that in a bit. But web, like the front end, now is on the road to introduce WebCrypto completely. And that changes things because unlike the case that I mentioned where you have to like interoperate between two services, this is way more common. It's more common for people having a Node.js backend interoperating with say, a front end with JavaScript. So it's a big target for interoperability, and we're working on that. And there's also boring SSL, which is something that Chromium and Electron use. And Electron uses it because it embeds Chromium. It's a very special target because Electron also embeds Node.js, and that means that we have to always make sure that the two are supported well. So, moving on, why crypto isn't easy? How many of you, for instance, have used the crypto API ever in the past? That's all of you, almost. And you might have noticed that it's not super easy to use. Like, it's sometimes very unintuitive, but that's the way it is. And some of you might be like, hey, stupid developers did not make good library. No, so this is a justification section, and there's a couple of reasons why crypto isn't easy. It's not easy because there's a lot of priorities. Ease of use is definitely one of them, but it's not the only one. So there's simplicity. We want the API to be as simple as possible, as bare bones and as primitive as possible. So, and simplicity does not exactly mean ease, as in Arch Linux is the most simple distro, but not the easiest one, right? And there's conventions, so we need to follow conventions and best practices in order to make sure that you're on the right side of things. Security and safety, obviously, being a big thing. Cannot compromise security of the cipher just to make it simpler to use. There's compatibility, so as we discussed in the last slide, just to make sure it's compatible with each other, but also at the same time, it needs to be backwards compatible. So that's one of the things that might come in the way, but it's really important, especially for enterprise, to have backwards compatible crypto. There is also feature completeness, so we need to expose as many features as we can, and WebCrypto compatibility. So talking about WebCrypto compatibility, it's one of the pain points that people might point out, and there's a lot of people who are like, yay, why is this not a big enough priority? And it's not that it's not a big enough priority. WebCrypto is, so for the uninitiated, WebCrypto is crypto built into the browser. It's a JavaScript API for crypto stuff. I don't know how to better describe it, sorry. But it's, as I said, it's one of the most common issues people pick up with Node.js is crypto. Why not make it super compatible? But there is a bottleneck, and there's a problem that, okay, firstly, as I said, it's a very high value target for interoperability, but the problem is that even though they're both just JavaScript, they're very different. Node.js and the browser are two very different platforms with very different goals and values. So saying it's just JavaScript, right? It's not the best thing to do. But that said, we are already on the road to interoperability. As you will see in the coming slides, there's been a lot of efforts to make sure that Node.js is completely interoperable with WebCrypto wherever it does not compromise with the other Node.js values. And it makes sense. Like WebCrypto has very different values. When I say that, I mean that, for example, it has a lot of focus on stuff like two-factor authentication. That's not something that you'd need too much with Node.js. This is like two different worlds, and they have very different end goals in mind. So one of the PRs that was made for key generation in Node.js was made by Tobias. You can find him on Twitter at Teeneason. So we at Node uses DER format to store keys. We've always used DER, but Tobias also chose to add PEM support just because WebCrypto does it. So that's moving ahead to on the road to interoperability. Then there's key objects. So that's about to land. I don't think that has landed yet in Node, but that will improve things quite a bit. And we're moving with much more things. We're planning much big things, and hopefully your life will be much easier if you're doing crypto on both ends. Now there's another thing that I wanted to talk about, and that is side channel attacks. Side channel attacks might be one of the reasons why some of the APIs might look a bit weird to you, but believe me, you do not want the APIs to have side channel attacks. So what is a side channel attack? It is a cryptographic attack that is not based on the weakness of the implemented algorithm. So you might have an algorithm that's like perfectly safe. It's perfectly fine to use that algorithm, but the implementation might leak some critical value that allows people to just completely break that algorithm. So even if it's completely safe, it does not matter in the end because some crucial information was leaked. And in order to avoid that, we might have to do a few extra things, put a few extra spanners in the way. One of them is a cache attack. So you might have heard about people reading the cache and figuring out what happened behind the scenes. There's a timing attack where people would calculate the time it took to do certain buffer operations. For example, finding out if two buffers are equal. That is something that depends on the size of the buffers, right? So if a buffer is twice as big, it will take twice as long to compute it or compare it with another buffer. So people would calculate the time needed and would completely break all the stuff because they now know what the key size is, for example. To avoid that, crypto has a API method. It's called crypto.timingSafeEqual. If you pass in two buffers, no matter how big they are, it will always give the result in constant time. And that's a nice thing. That thwarts all timing attack. There's also a power monitoring attack, which is kind of weird, but what a person might do would be to monitor what the power usage is and find out what the more intensive parts of an operation is, and then figure out a way to break the algorithm. And there's quite a few more, but I think you got the idea that we do not want to have any side channel attacks, and there has been quite a few in other crypto systems, and that's why we tend to play conservatively. Now, why not to roll out your own crypto? Like, why do we use something like OpenSSL? Why not just make our own crypto, maybe in the JavaScript? And why should you not use a NPM module that does crypto all by themselves? And hopefully you'll appreciate the beauty and pragmatism behind using OpenSSL by the end of this section. But yeah, so building crypto systems is hard, in case you didn't notice. But you know what's harder? Building secure crypto systems. It's very difficult to get in place. And what we do instead is we build on top of a barrel-tested foundation, which is OpenSSL. It's robust, it's barrel-tested, and it just works. So just to put this in perspective, Bob Bryan says, did I ever tell you about the do-it-yourself surgery I performed on my late mother-in-law? Everything went fine until she went and dead. And that's the point. Like, if you were sick, you wouldn't go to an amateur doctor because you care about your life, right? If you wanted a lock for your home, you wouldn't make your own lock or buy a lock from an amateur locksmith. because you care about the security of your house. But why would you then trust the security of your, say, multi-billion-dollar corporation in the hands of an amateur cryptographer? It makes no sense. Go with the experts, especially when the experts give away their tools for free, which is OpenSSL or other big libraries. So don't make your own crypto. I did compile a small hall of shame for some people who did make their own crypto and fell face first. So there's IOTA, who made a hashing algorithm called curl. They figured out that they were like too special or something, and they didn't use a perfectly good SHA-2 or SHA-3 algorithm. And what happened was it broke as soon as somebody took a look at it. It was that bad. And well, just to let you know, I have links and stuff for all of these. Meet me in the discussion zone if you want to inquire more about any of these, because things are going to get much more real. Telegram. You love Telegram. I know Russia loves Telegram, sorry. But Telegram, and funnily enough, so Telegram is the only person who comes in twice. And they've had a history of doing stuff that are not good cryptographically. But the first thing is empty proto. Instead of using a perfectly good off-the-shelf crypto system, they made one themselves. They decided to home roll a crypto system, called it empty proto. It was completely broken. They held a crypto cracking contest, but like rigged it in their favor, and it did not work out in the end. There are so many papers that I have here in the notes that have like very practical attacks on Telegram. And they've updated empty proto to use a version that's probably a bit more secure now. But that was not a great idea to use it in the first place. There's also encrypted profiles. So you're all old Telegram users. You know that they launched a feature called Passport, which is like encrypted profiles. You encrypt your profile. But the problem was that nobody apparently told them that you should not use a hash algorithm as a key derivation function. And they used just a hashing algorithm to generate keys, and it ended up weakly. They have had really weak symmetric keys for encrypted profiles, and there's a lot of attacks and proof of concepts to demonstrate how bad that went for them. But enough about Telegram. So there's a company called Mefair, if I'm pronouncing it right. It's IoT stuff, and they have like they made a cryptographic algorithm called Crypto1, and it's interesting. It's one of the most funniest algorithms I saw. And so there's a lot of academic papers that criticize this algorithm. And one of the papers, and I quote, concludes with, the security of this cipher is therefore close to zero. So you do not want to do that either. There is SaltStack, which did their RSA implementation. If you do not know what RSA is, quickly, for reference, RSA is just like raising numbers to big primes and then taking the modulo, public-private key stuff. But the point is that SaltStack decided to choose their own, make their own RSA implementation. They chose 1 as the preferred prime number. So they were just taking the plain text and raising it to power 1, which was the exact same thing as this plain text, and did not encrypt anything at all. So that was a shit show, to say the least. And then there's WEP. So we've all used WEP in the past, and I think we've also known how easy it is to crack it. It's like a toddler with a computer could crack it in like an hour or so. And that is because it was, in a way, home-cooked. Nobody cared about it, and it used the RC4 algorithm, which it does work well, but not with key repetition. It suffers from a similar key attack. And the problem was that because they used 24-bit IVs, which were not big enough, if you flood everything, it just breaks. So that's how secure these ciphers are. It's completely safe house. And the security of those ciphers, it's over 9,000. So talking about OpenSSL, it's robust, commercial grade, and full-featured toolkit. It's a great cryptographic library. It's built and scrutinized by experts, if you didn't notice. And we should trust the ecosystem as the rest of the ecosystem does. So Python's hashlib uses OpenSSL. Ruby's crypto module, and I'm not shitting you, is named OpenSSL. It's the default crypto module in Ruby. And please don't build your own. So go and Rust, build your own cryptographic libraries. And it's funny how, so I have this article that I might share to you later. But it's an article from the Go team where they actually say that they do not suggest people use a subset of their, primitives because they're not well tested. Well, of course they aren't. Also, it's fast, like really fast. So, and then I'd have to warn you, the graphs are a bit old, but I probably would have to plot my own graphs for up-to-date stuff. So I was like, you know what, just proving a point. It's the fastest for ES, it's the greenish one at the top. It's the fastest for triple-S by a very fair margin. And it was pretty damn fast for everything else. So that's Blowfish and Castpipe. It's probably among the top 2, top 3. And it's also the most popular. So it's the green curve you see. Its popularity is always rising. So moving on to the actual core of the talk, the state of crypto. What's happening? The past, the present, and the future of the crypto model. So we will talk about AE80. We support GCMs, CCM, and OCB mode. We'll talk about that quite a bit. There is AEAD. We've made a lot of, so that's the exact same thing. We made a lot of improvements to AEAD as well. We supported key generation really lately, and we'll discuss on what versions you can use that. And we deprecated createCipher, so that's something you noticed from the earlier slides. I'll tell you about that as well. And we have password-based KDFs, so that's a thing. And we have support for RSA, SSA, PSS. That helped nobody at all. But we'll move to what it actually is. So a quick timeline. So we have the fork era. It's like classical age or ancient age something. So we had AEAD GCM and PBKDF2 landing in the fork era between 0.x and 4.x. Then the forks merged, and we had Node.js. And in the past, we've had RSA, SSA, PSS, and we added CCM mode to AE80. And that's when we also did a documentation-only deprecation of createCipher. So it would still work, but it would show a warning. And, oh, sorry, it won't show a warning. In the documentation, you'll see a red stuff like, please don't use it. In the present, the stuff that we're working on between 10 and 11, there's AE80 OCB, so we added OCB mode. Thanks. We added support for key generation. createCipher was runtime deprecated, so you can't use it in a nice way at all. It'll soon be removed. And we added script support, so that's a successor of PBKDF. And there we added a lot of AE80 improvements. And what the future holds for you in and after 11.x is you have key objects landing, you have another thing coming to AE80, so that's good, and you have a lot more. So what is AE80? Like, what is AED? AE80 stands for Authenticated Encryption, so that's Authenticated Encryption and additional data. And AED is just authenticated additional data. So encryption plus authentication equals AED. That's convenient. Why do we do these together, though? We already discussed authentication and encryption before. It's just that it's way too common to be done separately. It's just way too convenient to have one thing do the both together in a nice way and secure way. How to use it? You could call the getAuth tag or the setAuth tag function on both cipher and decipher objects, or you could, if you just want to use AAD, you would do set AAD or set AAD on decipher. So that's nice. We support a couple of cipher modes right now. So there's GCM, which was added by Ingmar Runge. It landed in Node 0.11.10. The CCM mode added by Tobias. It landed in V10. It was semi-major for some reason. That's how things happen. OCB mode was also added by Tobias. It landed in 11, and because it was not semi-major, it was backported to 10.10. And there's Cha-Cha 20 with the Poly 1305 padding scheme, which was added by Yongxing Xu, and it should be, I'm sorry if I pronounce their name really badly, but it's coming soon, so it's probably not released yet. I hope not. It wasn't when I last checked. So how do you even do AAD? So there's three ways you could approach this problem. You could either encrypt and then MAC. So you could encrypt something, then call the hash function on the encrypted text. Just use that as the message authentication code and append that to the ciphertext. You could encrypt and MAC, like simultaneously, with no relation to each other, or then you could MAC first and then encrypt. You could do either of these. We also did a couple of improvements to this. So we allowed you to restrict valid GCM length, which is a nice thing to do. It's very highly recommended. And we could discuss all of this in the discussion area if you're more interested. It narrows down the list of valid tag lengths to a single value, which was added by Tobias in 10.12. And it also allows you to produce GCM tags with a specific length. These two go hand in hand. And it adds support for the auth length tag option, which you could specify. And it would lock down the valid authentication tags to a certain length. It was also added by Tobias in 10.2. Tobias had a lot of stuff. Thank you, Tobias. And it disallows multiple calls to set auth tag, and it makes a lot of sense. You shouldn't be able to set the authentication tag like over and over. You should just do it once. Yeah, it makes no sense whatsoever, and makes it very hard to detect bugs because you're doing it over and over again. This was also added by Tobias. But it landed in version 11 because it's semi-major, because it breaks existing code. Key generation, so we've been working on key generation. What is key generation? We talked about asymmetric keys, how you do that across the internet. There's now support for doing that like out of the box. So, and we support a lot of crypto systems because based on who you are, you might have a different preference. Do not tend to restrict anybody whatsoever. So there's RSA based, which is based on prime numbers basically, as we discussed. There's DSA, which is based on discrete logarithms. I'm not a math person. Please do not ask me how they work, although please do. And there's EC, which is elliptic curve based. So, and as I told you, we support DER alongside PEM for WebCrypto Compatibility, yay. And the functions you do to do that would be generate key pair and generate key pair sync as having the synchronous alternative. And it was also landed by Tobias in version 11, and it has been backported to version 10.12. So it's a quick matrix. You do not need to look at that for long. It's boring, but there's public RSA, private RSA, public DSA, private DSA, public EC, and private DC. The emojis make it easier. And then there's all these padding schemes, but there's also encrypted versions. So that's the log signifies the encrypted version. We supported a lot of these. Some of the crossed out ones are not doable or possible or needed, but if and when needed, we'll keep expanding this. So Prince Hamlet asks, IV or not to be? That is the question, and you might find yourself asking the exact same thing. So createCipher and createDecipher being deprecated because IVs are important. So on a note, the image on the right, that's Tux, the Linux mascot, but it's encrypted in OCB mode without a nonce or without an IV. And I thought that I could go on entire day telling you about how it's a bad idea to not use an IV, but this picture actually tells 1,000 words. You know how it's completely broken. There's no sense in encrypting it. It's just as if you did not encrypt it at all. So it adds security and randomness to your encryption, and createCipher may be insecure, like flat out insecure. You should not use it. Do not use it with CTR, GCM, or CCM modes, like flatly. Please do not. It's completely insecure. And also, if you're using IVs, do not reuse IVs, because that will cause vulnerabilities that you do not know about. They do not need to be secret. They only need to be unique and random. That's it. That's all you need to do. Use createCipher IV and createDecipher IV, please. We check the stats. There's a lot of people still using those two functions. Please don't. So we did a doc-only deprecation in 10, which was done by Tobias. And in 11, Tobias did a one-time deprecation. Hopefully, it should be removed by 12, but fingers crossed. So there's password-based key derivation functions. If you notice, I said something like PBKDF. So that's, what do? They derive a secure key using an insecure password. So a lot of us would like have a password. It's like, okay, password. It's like 2123. But that's not a good encrypting key. That's an okay password that you can remember, but it should not be used as a key. So what websites and stuff, other services would do, would be use this password in order to derive a key. And this is a technique which is called key stretching, and it just makes password cracking much more difficult using the concept of key stretching. So there's a couple of supported functions. PBKDF2, which is like the version 2 of the password-based key derivation function, that's what it stands for, has been here forever. It was implemented by PixelGlow, and it landed in 0.6, so that's a long time. That's like 10 years, maybe. And there's script, which was added by Ben Node.js in version 10.5, so thank you, Ben, as well. Script is really nice. You should try it out. And in the user land, you'll find at JoeP91, which is Sven Slutwig's script for humans. So that's an actually good NPM module that you should use, or could use at least. So there's RSA, PSS. What is it? It's a probabilistic padding scheme. So what do probabilistic padding schemes mean? Well, it's complicated, but that's like a lot of math stuff. Probably we'll discuss this after. But so think about it this way. It's like normal RSA, but only for signatures. But it's really good for signatures. Also, before, RSA used to do PKCS, version 1, version 1.5. It's much stronger than that. So the problem is that a lot of implemented ciphers are based on RSA, but the textbook RSA has much more security than them. So they have a security that is reducible to something which is below the RSA problem. This, on the other hand, has security reducible to the RSA problem. So it's like much more secure, and it's like one by one. It is an alternative to the PKCS version 1.5 in the sign and verify classes that we just used, and was added by Tobias in version 8. So that's it. I wanted to thank these people who made this possible. There's Tobias for doing all this work, Ben for always being a constant presence, Sven for helping out with the presentation, Anna and Shelly for helping me make this talk, Nikita for helping out with pretty much everything. Also wanted to thank the Node.js core collaborators for being awesome, and of course the HolyJS organizers. You've all been so great. And after all, thank you all.
Thank you. We have time for one question.
Hey, thank you. First, I'm going to explain why it's good practice for Golang to write own crypto library.
Okay.
First, to use C library OpenSSL, it's need to use C and unsafe package. As you know, inside C, you can get SIG files. Inside Go runtime, you cannot write it. Next, it's a good practice to improve compiling and performance for compiling team because they write a lot of intrinsics to compile simple functions to optimize the code on infrastructure that can be done on any RAM, x86 and another. That's all.
So thanks for the question. It's more like information, but thanks for the information. I do agree that like there's a lot of rationale behind them doing it. It's just like I didn't like the idea too much, but it's certainly a good idea maybe from their point of view. And also, so as you pointed out, it's very true. C has a lot of segfaults, and there could be segfaults in OpenSSL, but then that's not Go's problem. If OpenSSL has segfaults, then a lot other projects using OpenSSL will be hurt by it as well. So it should be up to OpenSSL to fix those. And if actually, so funnily enough, if Go used OpenSSL and discovered segfaults, that would actually help the entire community using OpenSSL. So because that bug would be fixed. But because they invented their own, now it's like they're on another island, and it's
another problems with OpenSSL. First, there is a log because you should stop whole Golang machine because you're calling C from Go runtime. It's first, it's a performance reason. And next, to use OpenSSL, you should link this dynamic link or static link to the language. But as you know, Golang is wrote on whole by Golang.
Yeah, Golang is written in Golang.
It's okay to use OpenSSL, for example, V8 and other JavaScript engines wrote in C++, and it's okay to use. But if you can see on the Go side, there is a reason why to write Open Cryptography library. Another super reason, it's Google, and they can write all on.
Google writes all their own code. And I do get your point. Like, it's perfectly fine for them to make it just like, does not help too much, should I say. And then at the same time, so it's not that there are no bindings for OpenSSL in Golang. There are people who have exposed bindings. As you said, they're just not efficient enough. And one of the reasons why they're not efficient enough is that there's a lot of these bindings, but like it's not a big enough priority, in my opinion, for the Go team to streamline that. For example, it was also like not efficient enough to do a lot of this stuff in JavaScript. V8 had a lot of problems, but they fixed that because it was the main target. But you know, people are now embedding V8 into Golang. That's Deno for you. I won't say it's good, but like, so it should be improved. And if they did it, they would have probably improved it.